It is an invited talk by John Fullerton. So John Fullerton is from Argonne National Lab, Illinois, United States. John is a postdoctoral researcher in the Functional Nanoscale Heterostructure Group in Argonne Material Science Division. He completed his PhD in 2022 from Queen's University, Ireland. And his current interest is knowing the formation and behavior of magnetic domains and topological spin texture in a range of magnetic nanostructures, including 2D ferromagnets, synthetic antiferromagnets, and 3D nanostructure. Today, John will talk about the complex spin texture in 3-dimensional nanohelix. John, you can please share your presentation.
That's perfect. So thank you so much for the introduction. So yes, my name is John Fullerton. I'm here from the Argonne National Laboratory. And I'd first like to thank the organizers for having me here to speak today. It's such an exciting conference, and I've really enjoyed seeing all the different talks throughout the day. So I'm excited to share with you some of our recent work on 3-dimensional nanohelices. So as an overview, I'll briefly give a bit of an introduction about why we want to move towards 3-dimensional nanostructures, and I'll talk a bit about the main fabrication technique we use to fabricate them, which is electron beam deposition, just for people who aren't maybe familiar with this yet. Then I'll move on to some of our experimental work. So first looking at the single nanohelices, where we use electron tomography and are able to link their magnetic behavior to their structural geometry that we're able to physically pattern. And then I'll finish off by talking about some X-ray tachography measurements of these double nanohelices, where we're able to tune and control magnetic behavior and ground states with geometry and material parameters. But so first, as I'm sure most of us are aware, there are lots of very important applications of nanomagnetism, largely in memory and computing devices. And perhaps most famous of which is the magnetic hard drive, where we're able to encode magnetic data as the form of up and down magnetic bits on a spinning hard disk. And sort of a lot of these devices have been very successful, but in recent years, we're starting to reach the limits of their computational power and efficiency. So people have begun working on proposing some future devices and looking at how we can make more energy efficient devices. So for example, there's the idea of this so-called racetrack memory, where we're encoding data as more complex spin textures. So for example, these synthetic antiferromagnetic racetracks, or as skyrmions and anti-skyrmions. And we're also able to potentially move these with currents instead of relying on mechanical motion, which can be a bit more, a bit less energy efficient. So in order for us to get to these more efficient and desirable devices, we maybe need a few developments along the way. So for example, we maybe need more advanced fabrication techniques that can allow us to access these more complex and more dense 3-dimensional architectures. And we also need ways to understand about how to form and control these intricate spin textures. And on the second point, people have looked at this in a number of ways, often with intrinsic effects, so for like crystal symmetry groups, or for interfacial effects in thin film multilayers. But specifically what I'll be talking about today is the idea of using geometry and physical curvature in order to control magnetism and induce desired effects. So there's been a range of these studies in the literature. So for example, people have looked at things and how we can influence and control domain walls. So it's been shown that curved nanowires can be used to initialize and pin domain walls and actually have a favorable chirality of certain domain walls as well. We've also seen that in cylindrical nanowires or nanotubes, you have this ultra-fast domain wall motion over what you see in planar lithographies. And in fact, in 3-dimensional and spiral type structures, you can have this automatic and free domain wall motion. So we have a range of properties that are quite promising and attractive when we're looking at building these future devices. Further to this, we can also have more complex spin and stray field textures forming through curvature and 3D magnetic nanostructures. So for example, there have been proposals on forming skyrmions using curvature. But I guess the main, these two examples at the bottom kind of bring me on to the main topic that I'll be talking about today, which is the idea of using these 3-dimensional nanohelices in order to control magnetization. So often you see these magnetization will be controlled by the shape anisotropy and will follow the helical path, or you can have more complex structures where you have interacting magnetic helices creating these locked pairs of domains walls. Now, in order for us to study these types of 3D and curved magnetic structures, there are a range of fabrication techniques people can use for electrodeposition, glancing angle deposition, etc. But the one I'm going to talk about today is known as focused electron beam induced deposition, or FEBID, which I think offers quite a unique platform in this field, as it almost works essentially like a nano 3D printer. And it works by injecting a precursor gas into the chamber of an electron microscope, which is then broken down by the electron beam in order to leave behind what is typically metallic deposits. Now, as in scanning electron microscopes, we have really fine control over the electron beam, so we can move it around in order to define the shape of our deposit. And this allows us to fabricate quite complex nanostructures. And so in recent years, there's been a lot of work on creating computer programs to help make this process more repeatable and more controlled. And just to name one, the one that I typically use is known as Feast. And so this essentially, again, acts like a way to make this a nano 3D printer. So you will create a 3D computer-aided design of your structure. You'll run it through the program, which will slice it up like so, which creates a set of instructions for your microscope. And then in doing so, you can then actually fabricate, a range of complex structures, essentially whatever you'd want. Now, so we show here quite fine, precise geometric control, like on the nanoscale, but maybe a key question to address here is, okay, what about the material properties of this? Are they actual, fully functional? What's going on here? So there are a range of precursor gases, and this is largely what defines what your material property at the end will going to be. And so largely what I'll talk about today is this cobalt carbonyl precursor, which is the most widely used when thinking about magnetics. And typically when we use this precursor, we can expect a resolution down to, say, between 60 and 100 nanometers, if we're looking at these nanowire-based architectures. We'd also expect, say, a cobalt content, which varies a little bit depending on our deposition parameters, so between, say, 75 to up to 95%. So we can get really high purity structures, but we can also vary this a little bit, which I'll talk about a bit later. And if we consider the microstructure of our deposits, they actually have this sort of amorphous nanocrystalline microstructure, which works well in this case as we sort of cancel out any of these magnetocrystalline effects, and we end up with quite a pure study of the geometry and the shape anisotropy, and how that then introduces, interacts with our magnetic spin textures. So all this to say, this allows us to design and fabricate these functional magnetic structures, which brings me on to the first kind of results section of our talk, where we're looking at this structure in question here, where we have a nanohelix with tighter helical spirals with height. So specifically what we want to do with this helix is we want to understand its physical structure and be able to link that to its magnetic behavior. So, I mean, what better way to understand its experimental structure than by using tomography? So we do this by acquiring a tilt series in our transmission electron microscope. We can then align all these images and calculate a full three-dimensional model of our nanostructure. And so here, this allows us to quantify and understand its 3D structure. So for example, we've colored this by its Gaussian surface curvature, which is just a measure of the curving of the local curving of the surface. So whether things are convex or concave, or whether we have these constrictions or surface bumps. And by plotting this out, say, over the height of the nanostructure, we can pick out locations where we have these bumps or where we have these constrictions, so we can understand the morphology and the shape of our nanostructure. And then, of course, we can also pick out other geometrical parameters. So, for example, the helical pitch, which we see decreases linearly with height. And this is the measure of the tightness of the helical spirals going up the structure. So we really have a platform where we can start to understand and quantify our geometry quite well. But as mentioned before, we want to be able to link that to the magnetism and the magnetic behavior. So to talk about that, the first thing we can do, experimentally at least, is to calculate its magnetic phase and look at what magnetic states we have. So we can do this with Lorentz TEM. So by taking a through focal series of images, we can then retrieve the experimental magnetic phase by separating out the electrostatic phase of the object using this pi-Lorentz software in order to calculate our magnetic induction of our nanowire. And the map can be sometimes tricky to read, so if we have these pink and blue alternating colors, is suggestive of this single domain state where we have all the spins following our helical geometry. But as we saw on the last slide, we have this full three-dimensional model of our nanowire. So what we can actually do is we can use that as an input for micromagnetic simulations in order to verify our experimental results. So this is an example here where we've taken our nanostructure from our tomographic reconstruction. We've inputted it into MUMAX3, and we've simulated, just say, a single domain state with all the spins in the negative direction along that helix axis. And we can compare the reconstructed magnetic phase with the simulated magnetic phase, and we get a good agreement here. So we can, we can verify these experimental measurements using our tomographic model. But we can also actually go a little bit further because we have these, working simulations based on our experimental geometry. So we can use that to actually go a bit further and simulate and predict our magnetic behavior. So as a quick example, we simulated the magnetic reversal process of this nanowire. So we started from our negative single domain states, and we're now applying a field in the positive Z direction. And we see that the reversal begins to be nucleated from this slightly thicker region down at the bottom, but then it very quickly propagates up through the majority of the structure. So you can see this sort of lower curvature region is prone to this kind of quite fast magnetic reversal and movement of domain walls. And we actually see we have this domain wall that forms towards the top end of the structure, as shown here. And this domain wall actually takes quite a large increase in fields in order to be expelled from the nanostructure. And that's because where it forms actually coincides with an area of increased Gaussian curvature, as we kind of saw earlier. So we can see that this actually acts as a pinning point and helps stabilize and form the domain walls and keep it there. So we can correlate this expected behavior back to our experimental geometry. So we have a few more details and looks at different structures in our recent works, but essentially this study allows us to look at this interplay between curvature and magnetism with a look towards these kind of domain wall type devices. So with that, I'd want to move on to the second main section of my talk, where we're looking at measuring the magnetism in double helices. So as mentioned earlier, we can create, quite intricate structures out of phabids. So that's what we're looking at here, is a more complex magnetic nanostructure. So this is a, computer model just to give you an idea of what the geometries look like and how we define things. So we have these intertwined helical nanowires with sort of a right-hand chirality at the bottom and a left-hand chirality at the top, which are joined and interfaced together. And this is something that we can replicate experimentally pretty well with good high resolution. And the nanostructure in this case is maybe about 150 nanometers wide. So, still quite small, and we're small enough so that our geometric chirality is going to have quite a big impact on our magnetic states. And to that end, for this system, we typically expect two remnant magnetic states that are potentially going to form in this system. So one, we term the vortex state, which essentially acts like a vortex tube, where both the helical arms are pointing in the same direction, and we have this circulation around, say, an axial core. And we'd also potentially expect, on the other end, an anti-parallel state, where we have actually the helical arms are now going against each other, and we form, two anti-parallel aligned helical domains with a domain wall in between. A key thing to maybe note here is that the magnetic chirality and the circulation of these two states is actually governed by the pattern geometric chirality. So we're showing these for left-handed states here, but if we had a right-handed double helix, we'd have the opposite type of circulation. So we see this kind of big influence of our geometry on the magnetic state. Now, so when we're looking at the system, as mentioned, one of these two states is going to be the ground state, and one is going to be a higher energy metastable state. So to look at which one is which and how we can tune this energy landscape, we're going to talk about a couple different parameters which decide which one ends up as the ground state and which one is more metastable. So one is the separation between nanowires. So this is essentially how much they're going to interact with each other. One is this helical pitch, as we talked about earlier, which is our sort of local curvature and twisting. And we're also going to look at the saturation magnetization, which is sort of a way to measure the cobalt content of our nanostructure, so how metallic it's going to be and how strong a magnetic response we expect. So using micromagnetic simulations, we mapped out these phase diagrams as a function, again, of pitch, separation, and saturation magnetization to say which state is going to be the ground state and what the relative energy differences are going to be. So when we have red or yellow or orange, this is where the vortex state is going to be the ground state. And when we have blue, this is where the anti-parallel state is going to be the ground state of our system. And we see that when we reduce all these parameters, so at low pitch at low separation and low saturation magnetization, this is where we further stabilize the vortex state. And at the other end, where we have high pitch or high separation and high saturation magnetization, this is where we stabilize the anti-parallel states over the two. And we have, areas where we have a good degeneracy between the two of them. So we see quite quickly here, we can really tune the energy landscape and the relative energy barrier in the system quite well using our geometry or with our material parameters. So one potential implication of this is, okay, how does this relative energy barrier size then affect our resulting magnetic behavior? So we're going to look experimentally now at two systems. So one here in the green cross, represented by the green cross over here, where we're still favoring the vortex state, but we're quite close to degeneracy with the anti-parallel states. So we're potentially looking at having coexistence of these two states. And then another one in this black cross here, where we have a very strong favoring of the vortex state. So to do this experimental work and to compare these two different systems, we used X-ray tachography, and this was done at the Hermes beam lane at Soleil in France. And so we're using circularly polarized X-rays, scanning it across our magnetic nanostructure. And in tachography, we would typically collect diffraction patterns at each scan spot. And this is then allows us to then reconstruct our sample in real space with very high resolution, so down to like 10 nanometers. And we're using this with circularly left and circularly right polarized lights in order to visualize the magnetic contrast, the magnetization in our sample. And in this setup, we're typically sensitive to the magnetic component along the X-ray beam, so which is going to be the circulation essentially of our magnetization. So from our two magnetic states, this is our expected magnetic contrast. So for the vortex state, we expect this quite clean transverse black to white or white to black signal, depending on the direction of circulation. With the anti-parallel state, we're expecting this opposite signal. So you have this alternating black and white contrast along the long axis of our wire. And we're going to be investigating this while applying magnetic fields along that long axis as well. So if we look first, say, at a branch of the major hysteresis loop for our high MS sample, so where we're sort of close to degeneracy between the two states. And as we start from negative saturation, where we have all this white color, and we slowly come back to remanence, we see we end up with these two vortex states where we have opposite circulation in the top and bottom of our helix. And this is just due to the opposite circulation of our geometry. So this is our geometry defining the circulation of our magnetic vortex. From here, as we continue to increase the field, we start to flip the nanostructure, and we end up going off to positive saturation. But it's in this region here we have this actual magnetic reversal happening, which we'll go through a bit slowly now. So schematically, what we can look at is we have this negative polarity down the center essentially, and we have this circulation around the outside. And as we increase the field, we actually fully flip this top helix into the opposite vortex state. But the bottom helix actually goes into this anti-parallel state where we have this alternating black-white contrast up and down, as we see here. And then as we increase the field some more, we then fully flip the magnetization. So we see that in this case, because of how we've engineered the structure and at what point in the energy landscape we are, we have this formation of an anti-parallel state to mediate that magnetic reversal. So we can then contrast this reversal with our lower MS sample, where we're really strongly favoring that vortex state. And if we pick out the area where the structure reverses, we see essentially no intermediate states form, and we just have a very quick reverse in saturation. So we can see this change in energy landscape hinders the formation of an anti-parallel state. So we're really able to tune what magnetic states appear in our system, and we can control, or we can favor the formation of certain states, or we can hinder those formations as well. So maybe just to summarize a little bit. So I've spoken about some of our work on single magnetic nanohelices, where we're looking at linking the magnetic behavior of the geometry through tomographic reconstructions. And we show how varying helical curvature and how varying surface curvature can lead to the formation and stabilization of domain walls and allows them to pin in places or to move quite quickly in places. So we begin to give quite a look about how you could potentially integrate these three-dimensional helical wires into devices and get the desired desired effects and desired performance from there. We then also looked at these double nanohelices, where we saw we could control this magnetic behavior and the energy landscape through the geometry and the material, and we can change how the reversal of the structure takes place. So we can change how the magnetic behavior of the system through this engineering. So we can decide whether we want certain states to appear or whether we want other states to appear. So we can really start to get an idea of how to control this magnetic behavior in quite complex 3D structures. So to wrap up, I'd like to just acknowledge some of the people who helped with this work, specifically my previous supervisors, Donald McLaren and Amalio Fernandez Pacheco, and of course, actually Naomi Leo, who is now at the Loughborough University, who've helped quite a lot with some of this work, especially in the double helices. I'd like to acknowledge the people at my current group in the nanoscale magnetic and electronic heterostructures group at the Argonne National Lab, specifically my supervisor Charadata Patak and Amanda Petford-Long for all their help and support here. And of course, I'd like to thank everyone here for listening and for your time. And I'd be happy to take any questions if there are any.
Thank you, John. Thank you so much for such a nice presentation about these 3D nanostructure that you said. So yeah, it's very nice. So yeah, we have time. We are open for the discussion or any question if someone has for John. So please unmute yourself or put the question in the chat box. Actually, I have one question, John. So, so the question is, how long it take for you to optimize this nanohelix? This looks a very challenging structure to fabricate. But it's not easy. It's not a simple nanostructure. It's a 3D nanostructure, and it's in a helical shape, not a single wire or a rod. So, how much optimization have you done?
Yeah, that's a great question. So I think maybe say a few years ago, when a lot of this was starting to be developed, this was quite a very, very challenging process and would take quite a long time. And I think it's still it's very dependent on the system you have. But I think once you actually understand the system, you can optimize the growth of a structure very, very quickly. So I mean, in just one session, you can go from sort of nothing to quite complex nanostructures. But yeah, I think as you maybe say, they are quite complex. So at the start, it was tricky, but then a lot of these computational programs make that a lot easier nowadays.
So this nanohelix, so you intentionally fabricate this nanohelix, or when you increase the length of this nanostructure, it becomes like curved. I mean, I want to know like mechanism of this. It's intentionally fabrication, or it's just naturally it becomes curved?
No, it's intentional fabrication.
Okay. And you used like before you use this planar structure, and then you focused electron beam to cut through the sample, right?
No, it's more like an additive process. So if you inject this precursor gas in, which will absorb to your substrate, and then the electron beam will then essentially break it open and will leave behind, say, just the cobalt in this case, and create little deposits. And then by scanning the electron beam, say, round in a helical-like fashion, you can create these spirals and these structures. So it's sort of like it's like a growth. It's like a 3D printing type process.
Because focused ion beam is the common technique, but this focused electron beam is, I never heard about this focused electron beam. So it's new information. It's a new thing called focused electron beam.
No, exactly. It's sort of a growing idea, I think.
Yeah. Okay. Yeah. Maybe I missed it somewhere. Yeah. So any other questions for John?
I have a question.
Okay,
so my question is about the material you choose. Why did you choose specifically cobalt to create these nanohelices? Does it have to do something with technique of how you fabricate them, or maybe you expected something?
Yeah, that's a good question. So I think cobalt for these kind of structures is the most widely used one, and that's because you can get these very, very pure structures. You can get nearly, say, 95, % pure structures. So you're kind of limited by the choice of precursor gas. So we've done other work with an iron precursor, which you can maybe get sort of similar structures, but is less mechanically stable. So the idea is we typically use cobalt as it's the most well-researched and the most known about, so it's the most easy for us to control. But you do start to see nowadays more precursors, the more options are coming out. So there's also like an iron cobalt ally that people have started using, that is showing promise. So it's sort of a growing field, really. So hopefully, as time goes on, you will have more material options.
Okay, thank you.
Any other questions? Okay, if not, then thank you, John, for such a very nice presentation.
Thank you.
Thank you so much.